There's a scene in the HBO TV series Silicon Valley, in which a tech billionaire called Gavin Belson, think a cross between Jeff Bezos, Sergey Brin, Peter Thiel and many others you're probably familiar with, hooks himself up to an intravenous drip.
And the quality won't be high until...
He does it in the middle of a pitch he's getting for investment from a young and now nervous founder.
Continue.
Okay.
The reason for this young founder's nerves is that the other end of Gavin Belson's IV drip is attached to a very young, handsome male model.
So, Gavin, Bryce is...
Very discreet. Keep going. This is great.
Is Bryce your assistant?
No, of course not. He's my transfusion associate.
When they're connected, blood starts to flow from the young man to the older Gavin Belson.
Are you really not familiar with parabiosis?
Can't say that I am.
Well, the science is actually pretty fascinating. Regular transfusions of the blood of a younger, physically fit donor can significantly retard the aging process.
It's a brief scene and it all sounds rather ridiculous. But there are two important truths buried in the fiction. First, parabiosis is real, at least in mice. It's actually a fascinating area of research, but a long, long way from being useful in people. The second, and arguably more important truth, is that Silicon Valley billionaires have spent years looking for ways to hack their bodies, to live for decades or even centuries longer. Their intentions might be far-fetched, but in funding real scientific work to understand how our bodies age, those billionaires' wild dreams could end up beneficial for everyone's health. Hello and welcome to Babbage from The Economist, our weekly podcast on science and technology. I'm Alok Jha, The Economist's science correspondent. Today, from regenerating organs to rejuvenating cells, we'll explore how to protect human bodies from the ravages of old age. We'll look at why we age and what it'll take for people to live even longer, even healthier lives. Humans are, on average, living much longer than they did a century ago. Life expectancy has been rising for decades thanks to everything from better medicine and nutrition to sanitation and more stable governments. In the rich world, the average life expectancy today is in excess of 70 years. And it keeps on going up by around 5 hours every day. It wasn't always like this in human history.
The norm until about 200 years ago was a lifespan of about 30.
Andrew Doig is a professor of biochemistry at Manchester University and the author of This Mortal Coil, A History of Death.
In Roman times, maybe you had a 50% chance of living to the age of 5. There were still some old people, of course. It was maybe 10% chance of living to be 70 or 80 in ancient Rome. What really changed, increased life expectancy, was in Victorian times, when Victorians, they were terrible doctors. They didn't have cures for diseases, but they were great engineers. And they built reservoirs and sewage systems, provided clean water. Malnutrition started to go away. People had better diets, they had better bodies. In 1900, still the biggest killers were infectious disease like tuberculosis, and measles was the biggest killer of under 5s, but life expectancy was up to 50. And then in the 20th century, total revolution happened where we defeated nearly all infectious diseases, brought in genuine cures like antibiotics, which came in the 40s and 50s after being developed in the Second World War. We got life expectancy up to 70, and now the average life expectancy in the world is 73.
Can we expect to see average lifespans go even further than 70, 80? I mean, is that feasible, do you think?
Countries with the highest lifespan in the world are some in southern Europe, like Spain and Italy, where it's well above 80. The highest life expectancies in the world are in East Asia, countries like Japan, where it's about 85. And it's so, of course, without any new inventions or anything, it's absolutely realistic for us to get to 85 and just by living like the Japanese. Going beyond that, we'll need some advances in medicine, and there are possibilities for real, genuine revolutions that could substantially increase life expectancy.
If people want to live routinely into their 90s and beyond, scientists need to get to grips with the underlying biology of the diseases that kill people in their old age. But what actually happens to a human body as it gets older? Someone who spent a career working on this question is Linda Partridge. She's the geneticist at University College London and also the founding director of the Max Planck Institute for the Biology of Aging in Germany. I asked her, why do we age?
For evolutionary reasons, because we're living in such a benign environment now, largely predator-free, good supply of food, very few physical hazards, much better conditions during development, we're basically living much, much longer than we did in our evolutionary past. So natural selection, which has honed, the development of the embryo, growth to adulthood, all of those processes, has not honed the later part of the human lifespan because it hasn't had a chance to. So things go wrong when we live beyond the time that we used to do for millennia of evolution.
So what are some of the biological mechanisms that we now are beginning to understand that cause aging?
So it almost certainly kicks off with things going wrong at the genetic level. So the genetic material itself can be damaged, the molecules that stick to it can go wrong. Sometimes they're there when they shouldn't be, sometimes they fall off when they should be. That alters the way that genes are expressed in cells. The whole machinery that controls expression of genes goes down. The major molecules in cells that do things, that make reactions happen, are the proteins, and the control of the protein domain fails. The synthesis of the proteins making them becomes less accurate. And then key bits of cells like the energy generators, the mitochondria, go wrong. Cells go through a process called senescence, which is turning out to be very important. So there's a type of cell called a senescent cell that's usually very important in development and wound healing. And normally the immune cells come along and remove those senescent cells when they've done their job. But that doesn't happen during aging, and they hang around, and they cause a lot of problems. And there's systemic inflammation, and cells fail to communicate with each other, and stem cells go wrong. Those are the key things. It's quite a long list, but we understand them pretty well now.
Should we view aging as a sort of root cause of many diseases?
Oh, yes, very much so. So if you look in humans at the really serious age-related diseases, neurodegenerative disease, particularly dementia, cancer, cardiovascular disease, you can see these aging processes present in the key tissues as they go through the aging process. And they're intimately wrapped up with causing age-related diseases. And it's really getting a lot of traction at the moment. People are very interested in the idea that these fundamental aging mechanisms, if we could combat them, we actually might prevent a lot of things going wrong simultaneously. And of course, that would be great.
Well, let's explore that a bit further. People are talking about rejuvenating cells or even regenerating organs or, even replacing blood plasma in some cases to sort of try and remove some of the effects of aging. How do you assess those approaches?
I think the one with the most promise at the moment is probably altering plasma because, of course, blood is so accessible. And if it's clear that either the particular types of molecules accumulate during aging and are harmful, or that things that should be present in blood are not there, and that's a problem, then it might be relatively easy to do something about that. I mean, that seems to me a plausible kind of idea. We've got no idea at the moment if it will work, I should hasten to add, but there is some very interesting work going on with plasma transplants. Originally those slightly Frankenstein parabiosis experiments where mice literally had their blood systems joined together were key in showing that if an old mouse is given a young blood supply, it actually improves the performance of its stem cells in multiple tissues. So there's clearly something interesting going on there. But at the moment, I think we're still very much at the discovery stage rather than something that could be implemented. And it's not clear whether it simply slow down the ageing process, possibly halt it. I think there's very little evidence at the moment that it would reverse it. I'm not saying it won't, there just isn't any evidence that it will.
Linda mentioned parabiosis there, which of course was what Silicon Valley's Gavin Belson was doing in our clip from the start of the show. There just might be something in the idea of hooking up an older person's bloodstream to that of a younger person, but it's very early days. Now, I need someone here to guide me through what's real and what's not, so I'm joined by Jeff Carr, The Economist's science and technology editor. Jeff, what we've heard so far is that ageing from a biological point of view involves the build-up of junk in the body and also our cells and organs wearing out and going wrong, all of which can lead to disease and eventually death. If scientists could combat some of those biological processes that lead to ageing, that could be the ticket to extending human lifespans, right? I mean, what are strategies that you think show some of the best progress in terms of slowing the march of time?
Well, it's a very complicated problem. If you're going to deal with ageing completely, if you were going to design an immortal human being, you'd probably have to start with the cell and you'd have to deal with an awful lot of different problems. But if you're looking at it as a medical patch to help people to live longer and rejuvenate their organs perhaps, one of the most promising approaches, the idea of cellular rejuvenation. And this uses 4 protein molecules called transcription factors, which were discovered by a chap called Yamanaka Shinya in Japan about 15 years ago. And these have this strange and wonderful property that if you apply them to a body cell, a cell which is differentiated to do a particular job, they will take it back to factory settings in a way. They will turn it back into something which closely resembles an embryonic stem cell, which is then capable of developing into other sorts of cells as a natural embryonic stem cell would.
Just take us back one step. Who was Yamanaka? Tell us who he was and what his role in this is.
So yeah, Yamanaka is a biologist in Japan. He still lives there. And he won a Nobel Prize for his work. It's very important work. Just to be able to create embryonic stem cells, pluripotent stem cells as they are known technically, has huge potential because it means that you can grow tissues in a laboratory. You can do a lot of the work which was very controversial 20 years ago. So if you want to test out medicine on a particular tissue, you can create the tissue. You could, in principle, test medicines on tissue that was identical to the person that you wanted to put the medicine into. But if you took a skin cell from them, turned it back into an induced pluripotent cell and then made whatever tissue it was that you wanted to run the drug on, you could look at its effects on the patient's tissue without ever having given it to the patient.
No wonder he won a Nobel Prize for that work then. How much have these methods been tested in the field of trying to rejuvenate cells then and turn them into something which might sort of reverse or counter some of the effects of ageing?
Well, the problem is if you do it too much and try to grow more than one tissue out of it, you can end up with things called teratomas. The teratoma is a type of tumour. It's a non-malignant tumour where tissues develop abnormally in an embryo. And these sometimes develop naturally in embryos where embryonic development goes wrong. But it's not the sort of thing that you would want in a medicine. But some of Yamanaka's followers did some experiments and discovered that if you just use very small and short applications of these factors, you can get around the teratoma problem. And also what is important from the point of ageing is that you can not de-differentiate, you can not reset the cell to factory settings. You can actually rejuvenate a cell without changing its property. You can make it younger, physiologically younger.
The proteins that Dr. Yamanaka found, also known as the Yamanaka factors, have been used by biologists all around the world to understand the physiology of how cells age and how that aging might be arrested.
In the aging field, there has been really exciting advances over the last 10 years or so. exploring what the consequences of aging are on the cellular, molecular, as well as physiologic level.
Heinrich Jasper is a director at GeneTech, a biotech company in California.
And one of the exciting observations was that epigenetic changes in aging tissues and aging cells can really drive a lot of the age-related pathology. And the correlate to this was that studies by Shinya Yamanaka originally showed that you can actually reverse epigenetic changes that have been imparted on cells by development, but potentially also by stress and aging, all the way to pluripotency.
Just last week, scientists at GeneTech, working with the Salk Institute in California, published results of a new study in which they showed that using Dr. Yamanaka's factors was a reliable way of slowing down the effects of aging in healthy mice.
We learned that in addition to individual tissue changes, there are systemic changes in terms of serometabolites that we identified. It seems as if metabolically the animal is becoming healthier or younger, if you want, after this treatment. And indeed, it seemed that animals that had experienced this partial reprogramming were able to repair skin wounds better than non-treated animals. I would say they definitely seem to be healthier. The expectation is that they would live healthier longer.
Now, these are still very early stage studies on the basic science of the aging process. And just because something interesting happens in mice, it doesn't always mean that the same thing will happen in people. We are vastly more complicated creatures, of course, but still, it's interesting.
The excitement here is demonstrating fundamentally that something that really 20 years ago was not even considered is ultimately something that can be achieved through very specific perturbations, right? I mean, the fact that you can reverse epigenetic marks of aging is something that had not really been imagined before the development of induced pluripotent stem cells. And so really following that discovery, there were ideas that this might be possible, but only now we're getting to a point where we are really now developing proof of concept that this is feasible. And so it's a really exciting starting point for more work.
Investors from Silicon Valley agree. Recently, a new startup was launched to look specifically at how to reverse aging in biological cells. Its name, Altos Labs. Jeff, you've written about Altos Labs in our Science and Technology section, haven't you? Just tell us what it is.
Altos Labs is an intriguing idea. It's probably the world's best financed startup company. It's acquired from various sources, some of which are known and some of which are unknown, $3 billion. And it's also acquired 3 research sites, one in Cambridge, one in Silicon Valley, and one in San Diego, which will be led by prominent researchers in the field. And they have a couple of big ideas, one of which is based on the Yamanaka factors and another on a thing called the integrated stress response.
We've mentioned Yamanaka factors already a little bit here. So are there specific targets that they're going for? Are there specific cells that they're going for in the research institutes at Altos that they'll be using the Yamanaka factors for?
The approaches are working in parallel. So they're not saying we'll use the Yamanaka factors for one thing and the integrated stress response for the other. But what they're aiming to deal with are diseases where the cells have gone AWOL, for want of a better word. So cognitive disorders, neurodegeneration, which would be things like Alzheimer's and Parkinson's, forms of diabetes, metabolic problems, cancer, and so on. And the idea is that by rejuvenating the cells with the Yamanaka factors and also by applying treatments to what is called the integrated stress response, they might be able to take cells that are behaving abnormally and make them behave normally. The integrated stress response is a natural phenomenon whereby cells that have moved outside their normal parameters are pulled back internally. Their protein manufacturing systems are reset to normal, and if that fails, then they are ordered to commit suicide so that they won't cause disease.
And how important do you think Altos is likely to be in this field? $3 billion is a lot of money. Does it deserve the excitement that people have in its founding?
I think it probably does, although I think it's perhaps been slightly misinterpreted. What they seem to be thinking of, ultimately the idea might be to prolong human life all round, but they seem to be trying to develop a novel approach to treatment for these diseases caused by cellular dysfunction. Then you can perhaps take this spectrum of old age diseases that might have an underlying organising principle behind them and develop treatments for them in ways which modern medicine doesn't do. That's the main business model.
And so the idea is to actually tackle these diseases rather than that sort of more fanciful idea of trying to extend life beyond what humans live to now. That sort of Silicon Valley billionaire dream of living forever or something.
So it's way more complicated, but what's interesting about aging is that there really does seem to be an underlying principle to it, which is that natural selection cares less and less about multicellular organisms as they get older and older. And so there's strong selection at the beginning. So when you spend time maturing and you're at the peak of your powers at the point where you become sexually reproductive. And from then on, I'm afraid it's all downhill. And all of these anti-aging propositions have to counterbalance the probably about 1 billion years since we started to get multicellular animals, which have just worked on this principle. It's a very hard ask, but that doesn't mean that you can't do important bits of it. And I think that's what Alsa's trying to do.
Rejuvenating cells is not the only anti-aging idea that's receiving a lot of attention. Scientists around the world are also looking at clearing out the junk that builds up in our bodies as we age, and fixing or even regrowing entire organs as well. That's all coming up. As people age, their organs grow weaker and become more prone to failure. And when they do fail, they take longer to recover and often never get back to their full strength. A good example is the heart.
If you have a heart attack, basically what happens is the lost tissue, of which can be very extensive, is not replaced, and instead a scar forms, and that scar causes loss of function because it's not contractile tissue.
Paul Riley is a British Heart Foundation Professor of Regenerative Medicine at the University of Oxford. What Paul does, and this is no exaggeration, is mend broken hearts.
So what the heart does to try and compensate for that is it remodels, and it undergoes a process of getting larger, expanding, the walls get thinner in an attempt to try and continue the efficient pumping of blood around the body. And ultimately what that can lead to is either susceptibility to a second heart attack or to heart failure over time. And heart transplantation is actually the only cure. But of course there are a dearth of donor hearts, and I think more importantly is that if you're fortunate enough to be a recipient of a donor heart, then you will be on toxic immune suppressive drugs for the rest of your life. And in fact, the life expectancy after heart transplantation is only 10 years. So if this happens relatively early in life, then clearly it's a significant problem for long-term and longevity.
So clearly we need something better as a solution. Tell me a bit about your work then. So what can you do to try and sort of make the heart repair itself more effectively than it normally does?
So what we're trying to do is to identify tractable cell types within the heart which can be stimulated to divide and contribute to lost cardiovascular tissues. And we base that on our understanding of how the heart forms in the first place. So during pregnancy and the development of the heart, we're very interested in the cell types that contribute to that process. And one such cell type is the epicardium, which surrounds the outside of the heart. During development, contributes to both new blood vessels and indeed even to heart muscle. And what we're interested then, of course, is to recapture that potential in the adult, because the epicardium is effectively dormant, goes to sleep in the adult setting. And with that, what we're keen to do is to restore the embryonic or developmental potential in that cell type to undergo, as it would do under heart formation, in what we would term heart reformation after injury.
So in a sense, the potential for the adult heart to fix itself is there somewhere. It's just not active. So have you had any success?
We have. We've been able to identify a sort of flagship protein that we published on a number of years ago called thymosin beta-4, which is able to activate these adult epicardial cells. And we showed that mechanistically it drives embryonic gene expression patterns, which give the cells back that potential that's lost during pregnancy. But we've also been using human primary cells from patients undergoing right coronary artery bypass. And we've used atrial appendage tissue, so little bypass tissue that we can collect during that surgery. And we've isolated primary human cells, and we've used those as a screening basis to find drugs that will stimulate these epicardial cells. And that's because the thymosin beta-4 protein is not an ideal drug. It has a very, very short half-life. It doesn't persist in the body particularly well. And so we've been looking for improved factors, and we found some of those in chemical screens and small molecule screens using these cell-based assays. And that's quite exciting in terms of the development of what we hope will be some future drugs.
So just walk me through what that looks like. So you're looking for a drug that kind of mimics what thymosin beta-4 does in the heart epicardium. So if somebody has a heart attack, they would take a pill or a drug of some sort to just reactivate their epicardium so that the heart fixes itself. Is that the goal?
Potentially. Interestingly, thymosin beta-4, at least in the animal studies that we carried out, had to be given before the heart attack. Interestingly, it didn't promote the same response if we gave it after the event, which suggests there needs to be some kind of priming of the cells. And so one of the things that we could think about is identifying patients at high risk, whether they've got a family history of heart disease, whether they have hypertension. And in theory, we could provide a drug such as a pill in an ideal world, which might prime these cells should an event happen. An alternative to that is we might find drugs which can stimulate after the event. And it's possible when heart attack patients come to the cath lab or the clinic to have their blood vessel reopened to restore blood flow in those first couple of hours after the event, that's an opportunity to administer a drug that might be long-lasting directly into the heart through the open blood vessel. So there is a possibility for that, which would tap into existing clinical practice.
So the work you described so far, Paul, is for a long time people thought that heart tissue could never be regrown. It was something that's impossible to sort of fix once it's broken. And clearly you've shown that that's not true, and that there's probably going to be other discoveries that show you can regrow parts of the heart. Is this more science fiction idea of managing to regrow hearts entirely, is that something that you think will happen one day? Or is it something that we don't need to shoot for if we've got technologies like yours that can fix damage caused by heart attacks and that kind of damage?
I think at the moment there's a big push, not just in cardiovascular, but in neuroscience and elsewhere, looking at the formation of organoids. And organoids are sort of as they sound, really. They're small organs in a dish, and the potential for regrowth of organs. But of course, that's extremely complicated because it's not just one or two cell types. There are multiple cell types. There's a vasculature and there's innervation as well, of course. You know, in terms of the heart, there's the conduction system that ensures that you have rhythmic contractility. And there's even the sympathetic nervous system, which ensures the sort of flight-fright response. So it makes it very, very complex and very challenging to think about deriving a heart in a dish. So at the moment, we're a long, long way from that. I would say organoids and that type of approach yet is early days, particularly in the cardiovascular field.
So I think that the message here is that from the point of the heart being completely inscrutable to science a few decades ago in terms of like repairing it and things, to, you know, maybe by the middle of this century, it's an organ that can be repaired, perhaps regrown. Is that sort of feasible? Is that something that's wild speculation?
No, not at all. I think that there are a number of different avenues, and our work's only one component of that, and there's some extremely exciting data out there. There are many groups worldwide working on this, and with the sort of combined efforts, I think this is very, very exciting.
Upgrading human body parts might still be some way off, but it's far less outlandish than it seemed even a decade ago. Another promising way to halt or even reverse the aging process could involve clearing out from the body what are known as senescent cells.
Senescent cells are cells that accumulate in your body as you age. They're dysfunctional cells. They're found in all organ systems. And These are cells that can cause damage to neighboring cells and eventually drive the risk of disease or disease progression.
That's Anirvan Ghosh, the chief executive of Unity Biotechnology, a startup based in California that designs therapeutics for diseases related to aging.
So when you look at aging,